How the world's tallest skyscraper was built. By the end of the 20th century, the race to build the world's tallest skyscraper claimed to hold. Each new contender was always slightly taller than the one before, and architects were running out of ways to top their previous effort. But in 2004, construction began on the new building in Dubai, promising a revolutionary design that would dwarf competition. In 2009, the 820-meter Burj Khalifa was complete, surpassing the previous record holder by over 60%. So, what innovation allowed for such a huge leap in height? For most of architecture history, heavy building materials made it difficult for tall buildings to support their own weight. To compensate, taller structures had a wider, thicker masonry at the base, making them substantially more expensive. The arrival of industrial steel in the early 20th century helped buildings shape weight and stretch to new heights, but steel frames require intensive labor to produce, often under poor working conditions, and when they are finished, these three-dimensional grid took up huge amount of space inside buildings. Tall steel skyscrapers also had larger, less dense surfaces, making them vulnerable to strong winds. Architects designed various countermeasures to prevent weight and structural damage, but to increase the height further, engineers have to completely rethink how tall a building was designed. Enter the father of modern skyscraper, Fajr Rahman Khan. This Bangladeshi American engineer believed tall structures should bear their weight where they are widest and most stable on the outside. Keep a porous, swapping an internal grid of steel beams. For a steel and concrete exoskeleton that would make the building more resilient to wind, while using far less heavy materials. Khan developed this idea into what he called tubular designs. These buildings have exterior steel frames that were braced with concrete and connected to horizontal floor beams. Tubular frame proved superior at absorbing and transferring the force of wind to the building's foundation. And since the exterior wall could bear the bulk of the load, internal supporting columns could be removed to maximize space. Following the 1960s, tubular design became the industry standard. This new philosophy allows for construction of taller, sturdier skyscrapers, including many of the record holders for world's tallest building. But planning the Burj Khalifa would take one more innovation. In 2004, the late Fazil Khan's longtime employers, Skimmer Owing Mero, completed the Tower Place 3 in South Korea. This building took Khan's exoskeleton design one step further, with the central column supported by three floating wings. Each wing's weight carried the other two, while the heavy concrete core acted as the support beam that also housed the building elevator and mechanical structure. This design, called buttressed core, allowed the entire structure to work as a single load-bearing unit, supporting the building's 75 stories. SOM was confident the buttressed core could support a much taller building, and they were determined to see how high they could go with their next project. As only the second building to use this design, the Burj Khalifa spans an unprecedented 163 floors. To battle the monumental vertical lateral forces, the design strategies placed the strongest load-bearing areas where the wind is also most powerful. Additionally, the Y-shaped layout was especially corrugated to minimize local wind forces. Every several floors, one of the wings proceeds slightly, forming a series of setbacks in a clockwise pattern. This spider shape disperses air currents, transforming 240 km per hour wind into almost gust. Considering its height and unique design, the Burj Khalifa was completed in a straggling short 5-year period. However, this pace came at a great human cost. The workforce consists mostly of South Asian migrants, but regularly do a shift over 20 hours long for a daily wage of roughly $10. Those who tried to quickly return home had their pictures and passports withheld by the project's construction company. These abuse conditions led to multiple protests, in addition to at least one suicide and one fatal accident reported on site. In the years following the tower's completion, the United Arab Emirates fell under harsh scrutiny for failing to enforce worker protection laws. Hopefully, future projects will prioritize the individuals behind its engineering marvels over the building themselves. One more. By the end of the 20th century, the race to building world's tallest skyscraper grinded to a halt. Each new contender was only slightly taller than the one before, and the architects were running out of ways to top their previous effort. But in 2004, construction began on a new building in Dubai, promising a revolutionary design that would dwarf for competition. In 2009, the 820-meter bridge keeper was complete, surpassing the previous record holder by over 60%. So, what innovation allowed for such a huge leap in height? For most of architectural history, heavy building materials made it difficult for tall buildings to support their own weight. To compensate, taller structures had wider, thicker masonry at the base, making them substantially more expensive. The arrival of industrial steel in the early 20th century helped the building shape weight and stretch to new heights. But steel frame required intensive labor to produce, often under poor working conditions. And when they were finished, this three-dimensional grid took up huge amount of space inside the buildings. Tall steel skyscrapers also had larger, less dense surfaces, making them vulnerable to strong winds. Architects designed various countermeasures to prevent wind and structural damage, but to increase the height further, engineers would have to completely rethink how tall buildings were designed. Enter the father of modern skyscraper, Father Rahman Khan. This Bangladesh American engineer believed tall structures should bear the weight where they were widest and most stable on the outside. He proposed swapping an internal grid of steel beams for a steel and concrete exoskeleton that would make the building more resilient to wind while using a far less heavy material. Khan developed this idea into what he called tubular design. These buildings have exterior steel frames that were braced with concrete that connect to horizontal fall beams. Tubular frame proved superior at absorbing and transferring the force of wind to the building's foundation. And since the exterior wall could bear the bulk of the load, internal supporting columns could be removed to maximize space. Following the 1916, tubular design became the industry standard. This new philosophy allowed for the construction of taller, sturdier skyscrapers, including many of the record holders for world's tallest building. But planning the Burj Khalifa would take one more innovation. In 2004, the laser Foxconn longtime employers, Skidmore Owings Merrill, completed the Tower Plaza 3 in South Korea. This building took Khan's exoskeleton design one step further, with a central column supported by three portrayal wings. Each wing's weight carried the other two, while the heavy concrete core acts as a support beam that also housed the building's elevator and the mechanical infrastructure. This design, called the buttress core, allowed the entire structure to work as a single load-bearing unit, supporting the building's 73 stories. SOM was confident the buttress core could support a much taller building, and they were determined to see how high they could go with their next project. As only the second building to use their design, The Burj Khalifa spent an unprecedented 163 floors. To better the monumental vertical and lateral forces, the design strategically placed in the strongest low-berry areas where the wind is also most powerful. Additionally, the Y-shaped layout was specifically calibrated to minimize local wind forces. Every set floor, one of the wing received slightly, following a series of setbacks in a clockwise pattern. This minor shift disperses air currents, transforming 203 km per hour wind into harmless gusts. Considering its height and unique design, the British Khalifa was completed in strikingly short 5 years period. However, this pace came at a great human cost. The workforce consists most of South Asian migrants. They regularly endure shifts over 12 hours long for a daily wage of roughly $10. Those who try to quickly return home had their paychecks and passport withheld by the project's construction company. This obvious condition led to multiple protests in Switzerland, one suicide, and one fatal accident reported on site. In the years following the tower completion, the United Arab Emirates fell under harsh scrutiny for failing to enforce worker protection laws. Hopefully, future projects will prioritize the individual behind these engineering marvels over the building themselves.